So for multiple regression, if we want to predict one dependent variable with multiple independent variables, we can do that in SPSS pretty easily. And for our class, we're going to use multiple regression to compare two different regression models, one in which we use several predictors and one in which we remove one or more predictors. So if we want to just look at how well a set of variables predicts a single dependent, just go down to linear regression. And in this case, we're using the the SAT scores and GPA data set that we have used last semester. So in this case, imagine that you're in admissions department and you want to know how well you can predict university GPA. So what a student ends with at the end of their time at a university using their entering data, so high school GPA, as well as their SAT math scores and their SAT verbal scores. And so we're going to set up a regression model here where we enter university GPA as our dependent and our SAT math and verbal scores and high school GPA as independents. So if you recall, for this data set, we have 101 participants or students who attended a large public university and were computer science majors. We have their final university GPA, their major GPA in computer science, as well as their high school GPA and SAT scores. So we only have students who not only applied, but also were accepted, ended up majoring in computer science and graduating. So it's a restricted data set. If you were in the admissions department, you'd be careful about generalizing to the applicant pool, but still it's an interesting question if we have this data. Okay, so imagine the question the admissions department wants to answer is, if we know high school GPA, do we really need to know SAT math scores and SAT verbal scores? To answer that question, we're going to construct a second regression model. So we're going to construct the first one that has all three predictors. Then we're going to move to next and set up a second regression model where we take SAT math and SAT verbal scores. And now in the second step, in the second model, we're going to, instead of entering them into the regression, we're going to remove them. And then for our purposes in this class, the only other thing we need to do is under statistics, then just select R-squared change. And for now, that's the only thing we're going to need. And hit continue. Then at that point you can hit OK and everything should be set up. So the first in our SPSS output window, what we'll see is that for Model 1 we were predicting university GPA, final GPA, using high school GPA, SAT verbal, and SAT math. In the second model, we did not enter any new variables, but we removed SAT math and SAT verbal. So now we're going to ask, how well does Model 1 predict university GPA? And then is the model significantly changed? Does it get worse or does it get better after we remove the SAT scores? Under Model Summary, we've got information about Model 1 and Model 2. Model 1 had an R-squared of 0.624. And when we remove the SAT scores, this dropped down to 0.608. So what you'd say is that the R-squared for Model 1 was 0.624, and so that our three predictors can explain 62% or 62.4% of the variability in university GPA, whereas if we use just high school GPA, we can explain 60.8, or almost 61%. Over in the change statistics, this is what we use to determine if the change, taking out a variable, had a significant effect. So for the first model, Model 1, the R-squared change is 0.624 because SPSS is calculating did the amount of variability change significantly once we entered any variables at all. So the change is to go from 0 before we had a model to 0.624 once we're using all three predictors. And yes, under most alphas, that would be considered significant. So the R-squared change, the probability that that change is actually 0, or comes from a distribution whose value is actually 0, it's quite small, 0.000. And to some long, you could check it out if you want. Yeah, this is going to be too slow. So anyway, what we really care about in this model, or in this, for this question is, if you're the admissions department, if we throw out the SAT scores, how does that affect our prediction? In this case, we drop from 0.624 down to 0.608, which is an R-squared change of negative 0.016. So we lose about 1.6% of our R-squared, the variability explained. And the significance, is this change large enough to believe it's actually different from 0? Under most standards, probably not. The significance of the change, the p-value, is 0.124. So the probability that we could get this size of a change, if in fact there really was no change, I get that about 12.4% of the time. For our course, when you're evaluating the R-squared change, we're going to adopt an alpha 0.05 as our criterion. So if that significance is below 0.05, we'll consider that to be a significant change in the model. And if it's above, we'll consider it to be not a significant change. For the ANOVA, as we mentioned in class, you don't need to worry about this for now, but basically you're testing, is the R-squared for each model significantly different from 0? In both cases, it is. And down below, you have coefficients for each of the regression models. So if you want to actually make a prediction, you can use these coefficients to construct the regression equation. So your predicted SAT score for Model 1 would be 0.579 plus 0.000 times a person's SAT math score plus 0.001 times their SAT verbal score plus 0.545 times their high school GPA. In Model 2, the constant changes and the coefficient for high school GPA changes, and so your prediction would simply be 1.097 plus 0.675 times the high school GPA. And so yeah, when we're doing the regression predictions, we're making a prediction about an individual case, we'll use the unstandardized coefficients in class. All right, so I think for now that's all that we'll need for class at this point. If you have any questions, please let me know.